So it should be recording now.
So welcome to the Geometry, Arithmetic, and Differential Equations periods seminar, the first talk of this year. So today we have Tiago Fonseca, who is going to talk about periods and Poincaré series. So Tiago, go ahead.
Thank you very much. Thank you for the invitation. And so in this talk, let me go straight to the subject. I'm gonna try to explain how to study this series here. So this is an infinite series having to do with Bessel functions and Closima sums. How to study them using algebraic geometry and to derive some arithmetic consequences of that. And these infinite series here, they appear naturally in the theory of modular forms. So that's where I want to start my talk, okay? So let me introduce some notation. So H, like that, is the upper half plane. So the open subset of C of complex numbers with positive imaginary part. And I'm gonna be looking in particular to the group, to the Hecke congruent subgroup, gamma naught of n, which is the subgroup of SL2 of Z of the matrices ABCD, where C is congruent to 0 modulo n. Okay, so this group acts on the upper half plane and have the classical action. So if you call this matrix gamma, so gamma acting on Z is AZ plus B over CZ plus D. Okay, so there is this action of this group on H, and then modular forms are functions, holomorphic functions on the upper half plane that transform in a certain way with respect to this action. Okay, so the notion I'm going to use in this talk is the following. So a weakly holomorphic modular form of weight k and level n will be a holomorphic function on the upper half plane, satisfying this transformation property. So this is the modularity property of weight k with respect to the action of the group gamma naught of n. And there's a further condition here, which is that this function should be meromorphic at the cusps. So I'm not gonna say precisely what this means now. It's gonna show up in a minute. But it's some growth condition at the boundary of the upper half plane. Okay, and if you replace meromorphic by holomorphic, you get holomorphic modular forms or just modular forms. Okay, and then weakly holomorphic modular forms of a fixed weight and level, they form a vector space, a complex vector space, and that's how we usually denote this vector space. Okay. All right, so this is just a definition. And then the natural question after that is, okay, how can you construct such functions? There's a very, very classical answer to that. Let me just admit someone. There's a classical answer to that, which goes back to Poincaré himself. And that is the method of Poincaré series. Okay. Before I continue, so let me just say, because I'm using this group, gamma naught of n, and the matrix minus identity lives here, this shows that there are no modular forms of odd weight. So in the sequence, the weight k is usually it's gonna be an even number. Okay. All right, so these are the Poincare series we're going to study today. So I'm going to take an even number k at least 4, and then m is an arbitrary integer. And then you can define the mth Poincare series of weight k and level n by averaging this exponential function here with respect to not the group itself, but some quotient of the group. So here I'm considering gamma naught of n, And I'm considering the quotient by this group that I call gamma infinity, which is the stabilizer of the cusp at infinity. So very concretely, this just means that it's a subgroup of gamma naught of n made of matrices where C is equal to 0. And these are all of this form. So the way they act on the upper half plane is just by translation by some integer. Okay? And then because of that, this shows that this sum here is well defined, because here you have e to the 2 pi I times an integer. So if you sum an integer here, you get the same thing. So this sum is actually well defined on this quotient. And then over Cz plus d to the k to get the transformation property I want. And then this condition on k ensures that this sum is absolutely convergent. And then you get, you can show you get weakly holomorphic modular form of weight k and level n. Okay? There's also a condition at infinity, which I'm omitting here. So just before I proceed to comments, you can also define a Poincare series of weight 2. But the problem is that if you just plug in 2 here, this doesn't converge absolutely. So you have to do something else, okay? But let me just say you can do that. And another comment is that if you take m is equal to 0, then you get another very classical family of modular forms called Einstein Series, okay? If you know what this means. All right, so, okay, now, all right, so again, this is a construction. Well, how can you see a modular form concretely? How can you put your hands on it? Now, there are different ways to do that, but usually in number theory, for instance, we are very much interested in their Fourier coefficients. So the fact is that a modular form is invariant under translation by 1. So you can write it as a series in Q. So this is classical notation. And Q is e to the 2 pi I z, an infinite series. But now, in principle, just this translation by 1 would say that this could have an infinite tail here. But the fact that it's meromorphic at the cusp, so in particular it's meromorphic at infinity, will say that the tail here is finite, so you get a finite tail Lorentz series in this case. And if it's a holomorphic modular form, then this is just, there are no negative terms here, okay? So this is Fourier series of a modular form. So these guys are called the Fourier coefficients. This is also called in number theory the Q expansion of a modular form. So to describe a modular form, you can just describe these coefficients here. Okay, so example, very simple one. So let's take k at least 4. And then, as I said, Poincare series of index 0 are Einstein series. So here I'm taking level 1 because it's more widely known. And then the Poincare series of index 0, weight k, and level 1 is just the normalized Einstein series of weight k, which is something that has a very classical Q expansion, which you can compute. And all of these numbers are integers, and this, so this is a Bernoulli number. This is an arithmetic function, the sum of kth minus 1 powers of divisors of n. And this defines a holomorphic modular form. Okay, so this is all very classical. It's just to say that you can compute, in some cases, the explicit Fourier expansion of modular forms. And then you have all these other natural examples. So you have the delta function. So this is some combination of Einstein series. And this is going to be a modular form of weight 12. And because they both have constant term equals to 1, it actually vanishes. It's not only holomorphic at infinity, but it vanishes at infinity. So this defines a cusp form. And this is classical notation for cusp forms. And then it has all sorts of interesting properties. So one of them is that you can find this.
Sorry, Tiago.
Sure.
I don't know if it is my problem or I'll have the problem. Are you showing now the delta function?
Yes.
But I'm just seeing the Einstein series. I don't know how it's for the other people. Here other people are saying the same problem.
Same problem. Okay.
They have, so we can just see the we don't see all the information that you are seeing in your screen.
It was better in full screen. Okay. The problem is that this full screen mode they cannot write, but it's all right.
Yeah. Anyway, if you are writing something, we are not seeing nothing of that. If you are writing, we can't see what you are writing.
Can you see it now?
Now, yes. Now it's example, now and if you go to this next example, it will be the delta function.
You can see everything.
Now is delta function. Yeah. Okay. Now you have to. Yeah.
Now it's funny because I can't see everything. So let me see. That's really strange.
I neither see all the page. I can see the delta function, the J function, and I just see the examples now.
Okay, so let's try to do that anyway. Okay. So now delta function. That's the formula for the delta function. And it's a very interesting modular form, and it's a cusp form, meaning that it vanishes at infinity. Okay. And then another very classical one is the J invariant, and that's the definition of the J invariant, if you can see that. So it's just E4 cubed over delta. And now you have something which has a pole at infinity, so it's a weakly holomorphic modular form. It's not holomorphic. And it's a weakly holomorphic modular form of weight 0. So it's invariant under the group. And then its Fourier coefficients are very interesting, and they show up in different parts of mathematics. Okay? All right, now a very cool thing about Poincare series is that they have a very special relation with Fourier coefficients of modular forms. So here's how you can phrase that. So there is a Hermitian product on the space of cusp forms called the Peterson product, which is given by this explicit integral here. So you take two cusp forms, so holomorphic modular forms which vanish at infinity, and then you consider this integral, and this defines a Hermitian product on this space. So this space is finite dimensional. And then Poincare series, they are a kernel for Fourier coefficients. So meaning that if you take the mth Fourier coefficient of a cusp form, this defines a linear functional on this cusp form. And this is this functional is representable by some form for this Hermitian inner product, and this form is precisely the Poincare series. So you can see the Poincare series as some kind of kernel function for this for the Fourier coefficients. Okay, and this formula has all sorts of consequences. One of them is that Poincare series generate. So if you take Poincare series of positive index, so they are cusp forms, and they generate the whole space of cusp forms. So in a way, if you study a Poincare series, you're studying all cusp forms. Okay? All right. Now, here are natural questions you can ask. So what about the Fourier coefficients of Poincare series themselves? Can you give explicit formulas like we had for Einstein series? And then what properties they satisfy? Are they interesting? Are they arithmetically interesting numbers or not? So again, this is a somewhat classical question and goes back to Poincare himself. And we do have explicit formulas for the Fourier coefficients of Poincare series. And here they are. So it's quite complicated. So the formulas for positive index are like this. So, so this is a holomorphic modular form. So there are no negative powers of Q here. And then the Fourier coefficients are given by some infinite series, making appear these guys here, which are Klosterman sums. I'm going to show the definition in a minute. And then values of Bessel functions. And for negative m, it's the same thing, except that now you have a truly weakly holomorphic modular form. So it has a pole at infinity. And the rest is more or less the same, except that this J Bessel function becomes this modified Bessel function, the I Bessel function. So this K, as I said, is a Klosterman sum. It's a real algebraic number. It's this exponential sum like this. And this J and I are classical Bessel functions. So I just took the pictures from Wikipedia just to show that they have a very different behavior. So the J Bessel function oscillates and decays, and the I Bessel function has some sort of exponential growth. Okay. Now, as I said, this is a very, very classical thing. It goes back to Poincaré himself. So this is Poincaré's last paper, where he studied Poincare series, and he computed the Fourier series of Poincare series, the Fourier expansion, and that's it here. So this guy is the Klosterman sum. And then he makes all sorts of interesting remarks. And then he goes on to compute the case where m is equal to 0, and his notation is p, where he recovers Einstein series. And then he remarks that this case is very different because the coefficients turn out to be integers, whereas here you have this crazy infinite series that have no reason whatsoever to be an algebraic number. Okay, now doesn't matter. So we have this explicit Fourier expansion, and one good thing about it is that you can put in a computer and just compute and see what you get. So for instance, if you take level 1 and weight 12, you can show that the first Poincare series would just be a multiple of this delta function. And the multiple is some transcendental number like that. And so all the Fourier coefficients are multiples of this transcendental number by some integer. Conversely, you can express the coefficients of the delta function as Fourier coefficients of Poincare series. And this is quite a funny thing to do. So there's a book of Sarnak where he, after making this remark, he says that this is the algebraic's nightmare because you replace integers, which are the Fourier coefficients of the delta function, by some crazy transcendental numbers. But it turns out this is very useful for some questions, and I'm gonna explain that in a minute. But another remark I want to make is that although you have this nice series of formula for the Fourier coefficient, this can be very hard to study. For instance, it's very hard to know when this coefficient is different from 0. So there's a famous conjecture, the theory of modular forms, Lemur's conjecture, and it's equivalent to showing that the mth Poincare series are not identically equal to 0 for positive m. Okay. Now, here's another example. Let's take now index, negative index and weight 2. So there are no modular forms, holomorphic modular forms of weight 2 and level 1, but there are weakly holomorphic modular forms. And this is an example. It's the derivative of the J function. Turns out this derivative is the same thing as this Poincaré series. So in this case, the coefficients of the Poincaré series, the Fourier coefficients, which are those that creates a series, turn out to be integers. And here are the integers. Okay. Now, a reason for studying that is that because Bessel functions are analytic functions, you understand well their growth behavior, and there are all sorts of theorems about estimating Klusterman sums. You can use that to estimate growth of coefficients of modular forms and weakly homomorphic modular forms. So using this fact here, you can, for instance, give a precise asymptotic formula for the growth of the Fourier coefficients of the J invariant, for instance. So this is one kind of things that Poincaré series can do for you. And then there are also other analytic applications. Okay. But again, they have a very erratic behavior. Although you have this nice formula, they have a very erratic behavior. So, so here in this case, they turn out to be integers. In some cases, they turn out to vanish identically. And here's another case that was studied much more recently, where they turn out to be integers, the Fourier coefficients of the Poincaré series. So here's the Poincaré series of index -1, weight 4, and level 9. So again, it's weakly holomorphic, has a pole, and the Fourier coefficients turn out to be integers. And this was studied in a paper of Grenier, Ono, and Rhodes in 2008, where they proved that these coefficients are integers using the theory of harmonic mass forms. And the proof uses the fact that, for those who know, the unique cusp form of weight 4 and level 9 has complex multiplication. And then some years later, Candelari, when he was investigating the theory of harmonic mass forms, trying to give a geometric interpretation to that, he, at the end of the paper, he mentions that you could sort of recover this statement by studying a certain cohomology group associated to modular forms. So this is a very strong indication that these Fourier coefficients of modular forms, they have a somewhat geometric nature. And this is a question you can ask in general. So, so one of the questions you can ask, so how do you explain this rationality phenomena? So these coefficients, they tend to be transcendental in general, but in some cases, they turn out to be rational numbers or even integers. And how can you try to explain that in general? And this also prompts the question, so is there a geometric interpretation for these Fourier coefficients of Poincaré series? And what can you do with that? All right, so there is a geometric interpretation, and because we are in a seminar about periods, you probably imagine what is coming up. So the notion of periods I'm going to use in this talk is this notion of Kontsevich and Zagier. So a period is a complex number whose real and imaginary parts are values of absolutely convergent integrals of rational functions with rational coefficients over domains in Rn given by polynomial inequalities with rational coefficients. So because you're imposing all this rationality here, this is a very arithmetic notion, okay? So that's the period. Whenever I mention period, I mean something like that. Now, this is a very nice elementary definition, but how do these numbers come about in algebraic geometry in practice? And they come about as follows. So take a smooth affine algebraic variety over Q, so something finite family of polynomials over Q, and then you consider the variety defined by them, and you impose that this variety is smooth, so maximal rank of the Jacobian. And then there are two cohomology theories you can, well, there are many cohomology theories you can study on such algebraic variety, but there are two that are relevant for periods, which are the algebraic de Rham cohomology and the Betti cohomology. So the algebraic de Rham cohomology, in this case, because I took my variety to be affine, is very easy to define. It's just what you think. So you take algebraic differential forms, closed algebraic differential forms, and then you mod out by exact forms, exact algebraic forms. Okay, so this defines a Q vector space, and that's the nth de Rham cohomology of X. Okay, and this vector space turned out to be finite dimensional, and then I'm just choosing a basis here because I'm going to use that in a minute. Okay, now the Betti cohomology, what people in arithmetic geometry like to call the Betti cohomology, is just the usual singular cohomology of the corresponding complex manifold. So you take the C points of that, you get a complex manifold, and then I compute the cohomology of that, the usual singular cohomology with Q coefficients. So it's the duo of the singular homology. And that's another Q vector space. And then again, I'm choosing a basis here. So it turns out, and this is actually quite surprising if you think about that, that these two spaces are isomorphic when you base change to C. So that's Grothendieck's theorem, also called the algebraic de Rham theorem, because it's just the analog of the de Rham theorem, which says that algebraic differential forms are enough to compute the cohomology of algebraic varieties. Okay. Now the periods, they appear when you compare these two cohomology theories using this map. So you just choose a Q basis of the de Rham cohomology, choose a Q basis of the Betti cohomology, and then you write the matrix of that in terms of this basis. And then you get what we call a period matrix. And then the coefficients of this matrix are periods in the sense of Comte-Wittgen's idea. Okay. And that's how we are going to use that. And here, when I mention motive, I'm just saying you can take this to mean in a very loose sense, just to be this collection of this vector space with this vector space and a comparison isomorphism between their complex extensions. Okay. All right. Now here's my claim, having recalled what periods means. So Fourier coefficients of Poincare series are all given by periods of modular motives. So this will be some kind of cohomology groups associated to modular curves. Okay. So particularly their periods. Now I'll be more precise than that later, but that's one way of thinking about this whole talk. It's just that the Fourier coefficients of Poincare series are given by periods of modular motives. All right, so before stating theorems, I want to give a very concrete example so you can see what's happening. Okay, so let's take the following elliptic curve. So given, so this is the affine equation for this elliptic curve. And okay, it is what it is. We consider this elliptic curve. And then it's an elliptic curve. We know how to compute cohomology of that. The de Rham cohomology has a very classical interpretation in terms of forms of the first, of the second kind, modulo exact forms. And so it will be two-dimensional, generated by a form of the first kind. So this is a holomorphic differential form, so an algebraic differential form defined over the whole elliptic curve. And this is a form of the second kind, has a pole and infinity, and the basis of the de Rham cohomology is given by the classes defined by these two forms. And the Betti cohomology, well, it's just the complex manifold associated to that is just a complex torus. So so it's generated by two closed paths, which I'm going to call gamma 1, gamma 2. I could be very precise. I could tell exactly what gamma 1 and gamma 2 are, but let's just take. Let's say I'm not gonna tell you precisely what these guys are. Okay, once you have a basis of the de Rham cohomology and a basis of the Betti cohomology, you can compute the period matrix. Again, this is a super classical object, so the period matrix will be something like that: omega 1, omega 2, eta 1, eta 2. So these, in classical terminology, these are the periods of the elliptic curve, and these are called the quasi-periods. And again, because this is a concrete example, you can tell what these cycles are, and then you can compute that numerically. That's the computation I did, and then you compute some numbers. All right, now here's the thing. So these numbers will tell me how to compute the Fourier coefficients of certain Poincare series. So here's one example. So the first Fourier coefficient of the first Poincare series of weight 2 and level 11. You can compute it numerically via the series formula, and you get this, and then you can verify numerically that this is equal to that. Okay, where omega 1 and omega 2 are these periods here. Now, this is actually classical. This formula actually follows from that kernel property. I told you the Poincare series satisfied their integral kernel for the Fourier coefficient. So this is not really new, but anyway, I just want to put it here. But there's also, you can also compute Fourier coefficients of Poincare series of a negative index. And here's a formula. Again, you take, I just took A1 just to give an example of the -1th Poincare series of weight 2 and level 11 again. You compute it, and then you can verify that it's equal precisely to that. Okay. So, so when I mean that Fourier coefficients of Poincare series are given by periods of modular motives, I mean that there are formulas like this. Okay? Yes.
These identities are experimental or rigorous?
They're rigorous. Yeah, I'm going to explain that. I'm just saying that you can verify that in practice. You can put the numbers on the computer and check that it's true. Okay.
What is the dimension of affine space?
Which space?
The affine X that you told in the theorem.
Oh, here is just like a general example. You mean that? It could be any dimension. It's just a general example.
So it's not. It doesn't need to be a elliptic curve of one
No,
dimension.
no, it could be an arbitrary smooth affine algebraic variety.
Okay.
And doesn't need to be affine also. It could be any variety. I just took affine to give this simple formula for the Durand cohomology. If it's not affine, it's a bit more complicated. Okay, so the elliptic curve precisely is not affine. But this case is kind of, so the cohomology of the elliptic curve, so the projective curve is also the cohomology of the affine elliptic curve, so given by this affine equation. So it's a bit easier.
Okay, thanks.
Any other question? So I'm gonna try to explain all these things now. All right, so let me first try to explain what these quantities are, because you see, these are some very specific combinations of the periods of this given elliptic curve. So let me explain what these things are. And now, so there's a very nice paper that came out in 2018 by Brown and Dupont, where they define what they call single-valued periods. So these single-valued periods are some particular example of periods that are given by one way to think about them. They're given by combinations of integrals of this form, so omega, wedge, eta bar for algebraic differential forms. Okay, but they do have a precise definition. So here's one way to go about that. So if you start with a variety like this, which is defined over Q, so Q is inside R, so there is a complex conjugation on the level of the points of the corresponding complex manifold. So this gives an involution, a continuous involution, which will act on the Betti cohomology, because the Betti cohomology is a topological invariant. And this gives this F infinity. So this is sometimes called the real Frobenius in number theory, or the Frobenius at infinity. This is just given by complex conjugation on the complex manifold. Now, when you transport this Frobenius, this real Frobenius, to the Durand cohomology via the comparison isomorphism, you get an involution of the Durand cohomology, the algebraic Durand cohomology, but you have to tensor with R. And this is what they call the single-valued involution. Okay. Now this thing goes from Durand to Durand. Okay. And now you define single-valued periods as you define periods. So it's just the matrix representing this involution when you choose a Q basis of Durand cohomology. And you can express this matrix in terms of a period matrix via this formula. So if you know how to compute a period matrix, to compute the single-valued period matrix, you apply this formula here. Okay. So this name single-valued period might seem a little strange because we're talking about numbers. So what is single-valued about numbers? But the reason they have this name is that this kind of appeared in the theory of, so if the periods depend on a parameter, so we're talking about period functions. So you have a family of algebraic varieties, and then you have a period function which solves the Poincare-Fuchs differential equation. So this function will give a multivalued function on the space of parameters. And this multivaluedness is related to the choice of the cycles on which you integrate to get this period function. So it's related to the choice of a Betti basis. When you do this process here, this thing, you sort of kill this choice, and now this depends solely on the RAM, and then you get a single-valued function. And so this appears in the theory of polylogarithms, and there are these single-valued polylogarithms, etc. And so this is a general framework in which you can do the the same single-valued yoga, you can also do that to numbers, and then you get these single-valued periods here. Okay, but again, these are very concrete things given by formulas like that. So, for instance, if you take an elliptic curve as before, so the cohomology is two-dimensional, so the period matrix is 2 by 2, and then you apply this formula here, you get that the single-valued period matrix is of this form. And these are precisely the quantities that appeared when I showed the example involving Poincaré series. Okay, so these are single-valued periods. Now I have to explain what that elliptic curve had to do with Poincare series of weight 2 and level 11. Okay, so here's something that is very general. So given a level n, you have a modular curve, y naught of n, which is an affine curve over Q, whose corresponding complex manifold is just taking the quotient of the upper half plane by this group, gamma naught of n. Okay, so this quotient admits another way of seeing that is that you consider this quotient and you get a Riemann surface, and this admits a Q structure. So this comes from an algebraic curve over Q, and that's the modular curve. Now, using these curves, you can associate certain motives, so certain cohomology groups, based on some constructions that you do over this curve. So, so to every weight k at least 2, and every level n, we're going to have a motive, which I'm going to denote in this talk. So this is not standard notation, mkn. This is a way of phrasing this motive, if you know what this means. So this is the modular curve, except that truly you should be talking about the modular stack of the curve. And then it's a cohomology over this modular curve with coefficients, with non-trivial coefficients. So the coefficients are in some kind of local system, which is a symmetric power of the cohomology, the relative cohomology of the universal elliptic curve. And then it's actually the cuspid or parabolic cohomology of that. So this is very complicated, but you should, it's just some piece of the cohomology of something like that. So you take this modular curve, and then you consider the universal elliptic curve. So the modular curve parameterizes elliptic curves. So there's a universal object living above it, which is an elliptic surface. And then you consider the self product of that with itself, the fiber product over the modular curve. You get a variety of dimension k minus 1. So this is sometimes called the Kuga-Sato variety. And then you can consider this k minus 1th cohomology, some cohomology group. And this motive is some subquotient of that, some piece of that cohomology group. Okay? Again, this is something that is very concrete, and I'm going to show later how to understand the Durham realization of that very concretely. Okay? All right, so so this, when I say modular motive, I mean something like that. Now, here's an example where these things are easy to understand. So let x naught of n be the compact, the projective modular curve. So it's just the compactification of y naught of n. Then this motive in weight 2, so m2n, is just the cohomology of this projective curve. Okay, so again, a motive for me is just a Durham vector, a vector space which corresponds to the Durham cohomology, a vector space which corresponds to Betti cohomology, and then a comparison isomorphism. And so this modular motive for weight 2 is just the cohomology of this modular curve. Okay. Now, in this example above, it turns out that this modular curve is that elliptic curve. Okay. So when you compute this modular curve explicitly, you get the equation for that elliptic curve. And that's why the Fourier coefficients of the Poincare series of weight 2 and level 11 are related to single valued periods of this motif, which is just this cohomology group. Okay, so you can guess now what is going to happen in general is that the Fourier coefficients of Poincare series of a fixed weight and level will be single valued periods of the corresponding motif of the same weight and level. Okay, so here's one general theorem you can phrase. So let S be a single valued period matrix with respect to a Q basis of the Durham realization of this motif. So I fix K and N, and this is a motif, so it's given by some cohomology of something. I choose a basis of the Durham cohomology, and then I can get a single valued period matrix. So it's given by those integrals. Well, then you can consider the field generated by all these guys that appear here in this matrix. Well, it turns out this field is the same field generated by the Fourier coefficients of all the Poincare series of the same weight and level. So this is telling that, although it's not telling which formulas are, this is telling that you can express these periods as combination of coefficients of Poincare series, and conversely, coefficients of Poincare series as combinations of these periods. Okay, so before I get more concrete, let me just mention two trivial consequences of the theorem like it's stated. So the first consequence is that this field is finitely generated. So here you have an infinite number of numbers, right? I mean, because M and N run through the set of integers. So this could a priori have infinite transcendence degree over a Q. But that's not the case. Actually, this field is finitely generated because this matrix just involves a finite number of numbers. Second consequence, a little bit of zerology here. So if this motif turns out to be trivial in the sense that it's zero, so
Tiago,
yes.
Is the first consequence easy to prove without going to motive language and so on?
Yeah, I think you can prove it. It shouldn't be too difficult to prove without this. Yeah.
These are your theorems, or?
Yes, I should put my name here, but yeah. Okay, so the second consequence is that if this motif is zero, so I'm going to mention in a minute a case where this happens, then all these Fourier coefficients will be rational numbers, because essentially, if this motif is zero, this matrix is the empty matrix, so you're not adjoining anything here. And then you get that all these Fourier coefficients are rational numbers. So a case where this happens is if you take level 1 and weight 2. So as we know, this motif is just the cohomology of the corresponding projective modular curve. But this curve, in this case, is just P1 and the cohomology is 0. And that's sort of an abstract explanation for why the Fourier coefficients of this Poincare series turn out to be rational numbers. Well, they're actually integers, but for this you have to work a little bit more. It doesn't follow from this. Okay. Again, this is something you can definitely prove without this without this whole business of periods. Okay, but I just wanted to mention that these things follow from this uniform statement here. Okay, now, okay, so this sort of answers a question in a way that these Fourier coefficients of Poincare series have geometric interpretation. They are all single-valued periods of some very specific motifs. Now, can you compute with that? Now, for that, you have to be a bit more precise. So, so let me explain how we understand the Durham realization of these motifs, of these modular motifs. So this is a theorem that it's one of those theorems that are well known to experts. So they appear everywhere in the literature. So I put some names here, but I'm not really sure who to attribute the theorem. But for us, it says the following: that the Durham realization of this modular motif here is given by a quotient of a space of weakly holomorphic cusp forms. So a weakly holomorphic cusp form is a weakly holomorphic modular form whose constant terms at the cusp vanish. Okay, just so for instance, the zeroth Fourier coefficient vanished. So it's given by the quotient of weakly holomorphic cusp forms, and this Q here means that I'm only taking rational coefficients. So the Fourier coefficients of these cusp forms are all rational. So this is a vector space over Q, and it's the quotient of that by this subspace given by an image of weakly holomorphic modular forms of weight 2 minus k for this differential operator, which is just the kth minus 1 power of this derivative here. So it's a classical theorem that this, when you consider this derivative, this differential operator, it will preserve modularity. So it will send this space to that space. And well, you can consider the quotient, and the quotient is precisely the Durham realization of this modular motif. Okay. So that's a concrete way of working with that. So for instance, if you take weight 2, which is the easiest case, so well, weakly holomorphic modular forms of weight 2 correspond to differential forms on the modular curve by the transformation property. And so, and then you can see that this quotient, weakly homomorphic modular forms of weight 2 modulo d of weakly homomorphic modular forms of weight 0, is just the Durham recipe for computing the cohomology. So this quotient gives the cohomology of the open modular curve. Now, if you consider the weakly homomorphic cusp forms, this will correspond to differential forms with vanishing residue at infinity along the cusps. And then you get the cohomology of the projective modular curve. Okay. Well, the proof for arbitrary k is some kind of generalization of that. All right, now, so here's some very explicit formulas, because that general thing, that identity of fields doesn't tell you how I got the formulas, for instance, in weight 2 and level 11. So here how we can get actual formulas. So let's take rank 2, so meaning that the realizations have dimension 2. And then let F and G be weakly homomorphic cusp forms, and I'm going to take F to be an actual cusp form, inducing a basis of the Durham realization. So the Durham realization of this motif is just the quotient of that by some subspace. So I can lift that to weakly homomorphic cusp forms. So I can actually choose two guys which induce this cohomology group. And then because this is rank 2, the corresponding single valued period matrix is 2 by 2. And then I take the single valued period matrix corresponding to that choice. And then here's a formula. Here are actual formulas you can prove. So, so this is another theorem. So for every n, so here positive, there is a weakly homomorphic modular form of A2 minus k with rational Fourier coefficients, and that's what is important here, such that now this guy won't appear here. So the nth Fourier coefficient of this Poincare series is up to this rational number given by 1 over this single valued period. And the Fourier coefficient of the Poincare series of negative index is up to this rational number and this rational number, a quotient of 2 single valued periods. Okay, and this, so these rational numbers are just given by Fourier coefficients of this cusp form F, which has Q Fourier coefficients, and this one involves also the Fourier coefficients of G, so the other guy inducing the basis, and of these HMs here. Now, it turns out that in concrete cases, if you plug in concrete K and N's, you can actually compute those guys. You can compute everything. And that's how I got the formulas in that case. So the formulas are provable, and they follow from that theorem. Okay. Now, yeah, I still have 5 minutes. So, okay. So this theorem is already telling you, for instance, some funny things. So, for instance, if you know that the nth Fourier coefficient of f, for instance, or the nth Fourier coefficient of f are 0, then this term will vanish. So this guy will be 0, and this term will vanish. So this guy will be a rational number. So it tells you precisely that when this guy is a rational number. Now, there's another funny thing which can happen, which is, so this will never be rational, although we cannot prove that. But this is in general a transcendental number. But this guy, this quotient, it can be rational. And when this quotient is rational, then this whole expression will always be a rational number. And that has to do with this complex multiplication business I mentioned in the beginning. So let me just briefly, very briefly explain how you understand that in this geometric framework. So a complex multiplication by this quadratic imaginary field here means that this motive admits some non-trivial endomorphism. So it's going to be, if you just think about the realization, it's just some vector spaces endomorphisms which are compatible with the comparison isomorphism. And then when you write what this means, you get a matrix. Sorry, this K should be L. You got a matrix A, B, C, D, and the fact that C is 0 has to do with the Hodge filtration of the motive. So you get a matrix A, B, 0, D, satisfying this commutation property with respect to the single valued period matrix. And this tells you linear relations between the single valued periods. So this implies, if you write down what this means, this implies that this quotient is given by something like that. So all these guys live in L, but all these guys are real. So this lives in L intersection with R, which is just Q. And so when you have complex multiplication, this quotient turns out to be a rational number, which implies that the Fourier coefficients of the corresponding Poincare series are all rational. And so that's the case we had before in weight 4 and level 9. So this motif, you can prove it has CM by this field. And the corollary is that the Poincare series of negative index will have rational Fourier coefficients. Okay, so I have 1 minute left. If you allow me 3 minutes, I'm just gonna say a few words of how you prove those theorems. Okay, so to prove it, you need to understand what, you need to give an explicit description of the single valued evolution for this modular motif here. And this thing comes from the theory of harmonic mass forms. So something I mentioned in the beginning. And harmonic mass forms tell you how to express the single valued evolution concretely in terms of functions. So, so essentially the single valued evolution is given by considering what we call a harmonic lift of the modular form. So this space here is given by a quotient of a space of weakly homomorphic modular forms. So you take a class of a weakly homomorphic modular form here, and then you consider something called the harmonic lift of that. So this is now a function that is not holomorphic and satisfies this differential equation. And then you apply a differential operator to that. And that's the image. The class of that is the image under the single valued evolution. So it doesn't matter what these things are precisely, just that there is a very explicit way of understanding what the single valued evolution is in that case of modular motifs. And then the next ingredient I use is a theorem of Brinkman and Ono from 2007, which tell you what the harmonic lifts of Poincare series are. And this allows to prove that the single valued evolution on the image of the Poincare series in this cohomology group is just minus the Poincare series of the opposite index. And using that and then some linear algebra, you can prove the theorems I mentioned. Okay, and I'm gonna stop here. So let me just mention 2 things. So this is the paper with the theorems I showed you today. So this is the preprint of Brown and Dupont, where they developed this theory of single valued periods. It's a very nice paper. Really recommend it. And there's another source of inspiration for this work that I didn't mention in this talk, which were computations done by Broadhurst, and then here published by Akers and Broadhurst, on sunrise integrals, so in quantum field theory. And Broadhurst expresses these things in terms of what he calls Hadamard sums, and this turned out to be Fourier coefficients of Poincare series. And so he obtains experimentally some formulas like the ones I showed you today. And this paper was actually another inspiration I took for this work. All right, I'm gonna stop here. Thank you.
Okay, thank you, Tiago. Any question? Maybe I put 2 questions that I have. First, the Poincare series, they have some reasonable functional equation like modular form with respect to some subgroup of SL2C or SL2 something.
Sorry, can you repeat the question?
No, we have the classical functional equation for modular form with respect to the action of SL2Z on the upper half plane.
Mm-hmm.
I mean, is this, do we have something similar for this Poincare series in general?
I'm not sure if I understand what it means in general. I mean, these guys are modular forms, so they transform like that.
Oh, okay. No, this is Yeah, okay. These are okay. They are here.
Yeah.
I missed this. And
Yeah.
something also. At some point, you use. I mean, do they satisfy some reasonable differential equations also?
Differential equations among themselves, no, not that I know.
So in any way, one might define new functions like E2 in the case of a modular form, such that to be able to write down differential equation, I suppose.
Yeah, I see what you mean. Yeah, I never looked into that.
Okay. Okay. At the beginning, maybe Tiago, if you want to turn off recording.
Stop sharing so people can ask.
Okay.
No, I stopped sharing, but I didn't stop the recording.